A really important class of examples includes this example. Z with X inside, not parentheses, but square brackets. This symbol you're going to become very familiar with for the rest of the course. It's going to represent a polynomial ring. All polynomials in the variable X with integer coefficients. This is the set. As a set, it's all polynomials in the variable. I'm going to put the word variable in quotes because I'm also going to give it another name, or indeterminate X with integer coefficients. That's why there's the Z there, is to emphasize that the coefficients are integers. That's what it is as a set. This turns out to be a ring under ordinary polynomial addition and multiplication, as you've been doing polynomial and addition and multiplication since when? 8th grade? I'm not sure what grade they introduced it. This is a ring under ordinary addition and multiplication of polynomials, as you've always learned it. So what do I mean by ordinary addition and multiplication? Let's just do a quick example. You know, if you're going to multiply x squared plus 2x plus 1 times x minus 3, and then add, say, x cubed plus 3x squared. So I'm multiplying those two polynomials, and then whatever result I get, I'm going to add it to that polynomial. You do use the distributive property as if these quantities, these expressions represented numbers. We're not really saying they represent numbers, but you certainly can pretend that. So we'd have, for example, x squared times x is x cubed, plus 2x times x is plus 2x squared, plus 1 times x is plus x, and then take each term and multiply by -3. So we'd get a minus 3x squared and a minus 6x and a minus 3. Then don't forget to add x cubed plus 3x squared, and then simplify by combining like terms. So that's the corresponding powers of x. So we've got two terms that involve x cubed here and here. X cubed plus x cubed is 2x cubed. That takes care of the cube terms. What about the squared terms? There's 3 of them. The 2 on the right here cancel. Negative 3x squared and positive 3x squared. I'm left with just a plus 2x squared. Catch me if I make a mistake. Hopefully there's no mistake here. And then with the x terms, I've got an x and a minus 6x. So that's minus 5x minus 3. So I had effectively 3 elements. These are all elements of this polynomial ring. I combine them through multiplication and addition in the usual way to get another element of this polynomial ring. The original coefficients were integers. The answer has coefficients which are also integers. Why would this be a ring under these operations? Let's not prove it, but let's think about it briefly. To be a ring here again, this is a good reminder. Think with me here. It has to be an abelian group under addition. So when you add, first of all, it implies closure under addition. When you add 2 polynomials with integer coefficients, yes, you combine the like terms, you're still going to get integer coefficients. Closure happens, that's good. The associative property happens if you add 2 polynomials, use function notation. For 3 polynomials, f of x, g of x, and h of x, with parentheses around that one, you get the same thing if you put the parentheses around the second pair, g of x plus h of x. The associative property does work. I'm not proving that, but hopefully it's believable. I mean, this is true for arbitrary function addition as well. Doesn't have to be polynomial addition. If you do think of these things as being functions of a variable x that's a real number, say, then these function values are real numbers, integers even, if the coefficients are integers and if x is an integer. And whether you think of them as real numbers or integers, associativity happens with those things. So yes, it will end up happening here. That's not really a proof in the general setting, because when we talk about the polynomials, they're pure expressions that we don't have to think about the things that we're adding as being literal numbers. So it really takes a little bit more in general. Does it have an identity element? Yes, the zero polynomial, where all the coefficients are zero. As a function, it's a constant function. Graph is a horizontal line, that's the x-axis. Not that we have to think of it as a function. We could just think of it as just a symbol. A polynomial where all the coefficients are zero. Add that to any other polynomial, you're going to get that other polynomial. By the way, it's also an abelian group under addition. F of x plus g of x will equal g of x plus f of x. And every element has an additive inverse. F of x plus negative f of x is 0, where what is negative f of x? If you think of these as functions having outputs, it would be the opposite value of this as a number. If you think of them as pure symbols, pure polynomials, this is a polynomial obtained from this one by taking all the coefficients and negating them. Right? The additive inverse of 2x squared plus 3x minus 5 is negative 2x squared minus 3x plus 5. Okay, so it's an abelian group under addition. What is necessary for it to be a ring when you include the multiplication operation? It's got to be closed under multiplication. Multiply two polynomials with integer coefficients. Do you get another polynomial with integer coefficients? Yes, you do. You know, you can't think of an example where you don't. That's not a proof, but you really do. What else has to hold? The associative property has to hold for multiplication instead of addition. And distributive property has to hold. F of x times the sum g of x plus h of x does in fact equal f of x times g of x plus f of x times h of x. That's the left distributive property. A right distributive property holds as well. In fact, this is a commutative ring. F of x times g of x does equal g of x times f of x. Okay, that does end up happening. We don't call it an abelian ring. We call it a commutative ring. Does it have a unity? What do you think? Yeah, 1. What is that 1? Is it the number 1? Technically not. Okay, technically this was not the number 0, it was the polynomial 0. A polynomial, you could imagine it having x's in there, but all the coefficients are 0. This is technically not the number 1, it's the polynomial 1. A polynomial where all the coefficients are 0 except for the constant term, and the constant term's coefficient is 1, the number 1. But it's kind of, this might seem like it's just silly in a sense. You kind of can still think of it as the number 1 as well. And in fact, think of the integers as a subring of this zx. Technically, it's not, because technically the integers are numbers, whereas the elements of this are not numbers, though they do include constant polynomials whose only non-zero coefficient is the constant term. But the connection is so tight, algebraists usually do think of this can be thought of as a subring of zx, even though technically it's not. Algebraists usually think of it that way anyway. There's a little formalism you have to go through to make it official, to make this a bit more rigorous. But at an intuitive level, we can take any integer, which is a number, and think of it as a constant polynomial. Just a little sleight of hand, so to speak. This ring, this polynomial ring, in fact, we usually try to use that word polynomial. This polynomial ring is a fairly nice ring. Weird things don't happen. In particular, if you have a polynomial like this, x squared, let's say minus 5x plus 6, and you're wondering, let's imagine plugging in numbers into this. Does this have integer roots? Zeros? Does this equation have solutions? You know, since what, 8th, 9th grade, that you can try to solve this by factoring, or the quadratic formula. But I did make this one so you can factor it as x minus 2 times x minus 3. And you know that in looking at this equation, the solutions are x equals 2 or x equals 3. You know that this ring has no zero divisors. What do I mean by that? Zero divisors are an example of something weird that can happen in some rings. As a simple example, Z4, we talked about this last time. In Z4, which consists of the elements 0, 1, 2, and 3 under addition and multiplication mod 4, weird things can happen, such as the fact that 2 squared is 4 is 0. Hey, 2 is nilpotent. And 2 is a zero divisor. This equation, 2 times 2 equaling 0, would mean 2 divides 0. 0 is divisible by 2. We could write 2 divides 0. There's a non-zero element I can multiply 2 by to get 0 itself, in fact. Weird. But that doesn't happen in the integers. If you got the product of two integers being 0, I'm restricting myself to thinking of x as an integer here. X is an integer when I imagine plugging in numbers for x. If I got the product of two integers being 0, one or the other factor has to be 0. X minus 2 is 0, or x minus 3 is 0. Which means there's two solutions, x equals 2 or x equals 3. I'm using the word or with the implications here in the way that they are, but it is also true that both x equals 2 and x equals 3 are solutions. This line of logic effectively shows that 2 and 3 are the only possible solutions. If I've got an equation like this, I'm wondering what are the possible solutions. These implications imply that if x is a solution, then x must be 2 or 3. But it's also true that both numbers, 2 and 3, solve this equation. But in other rings with zero divisors, sometimes quadratic equations have more than 2 solutions. I don't know what this one does offhand, but there was an example in the book. See if I can find it. Consider the polynomial x squared minus 4x plus 3 as an element of another polynomial ring, Z12x, where the coefficients are elements of Z12. Now, technically speaking, to be precise about how this could possibly be an element of Z12x, I need all the coefficients to be numbers between 0 and 11, right? The elements of Z12 are technically 0, 1, 2, 3, etc. through 11. But I have a -4 there as that coefficient. Technically speaking, this equals x squared plus 8x plus 3 mod 12. -4 can get replaced by +8, effectively thinking of them as being equivalent symbols for the same thing in Z12. There's an equivalence relation going on in the background here. Consider this polynomial in Z12x. By the way, you can factor this as x minus 3 times x minus 1. It certainly has 1 and 3 as roots, but it's actually got more. It turns out the other roots are 7 and 9. For example, if x is 7, plug it into the factored form, you get 7 minus 3 is 4, and 7 minus 1 is 6. Oops, wrote the wrong thing there. 7 minus 3 is 4, and 7 minus 1 is 6. 24, but mod 12, that's 0. I just plugged it into the factored form there. And it also has another solution, x equals 9. If you plug that into the factored form, 9 minus 3 is 6. 9 minus 1 is 8. 6 times 8 is 48, but that's 0 mod 12. You would get 0 if you plugged it into the unfactored form as well in either of these forms. This quadratic polynomial in this polynomial ring, this is a polynomial ring here. Once again, the elements are polynomials, but now the coefficients are all from Z12, so they're all in standard form, at least 0 through 11. Under ordinary addition and multiplication mod 12, even though it's a quadratic second degree, it's got 4 solutions: 1, 3, 7, and 9. Weird. Once again, emphasizing we want to be aware of weird things that can happen, though it's not our main point of emphasis. The integers z, the integers mod p, where p is prime, zx, and zpx, where once again p is prime. P is prime in both cases. Are special rings with a special name. They're called integral domains. I said general ring theory is pretty weird. We want to be aware of weird examples, though it's not our main point of emphasis. But there are 2 special kinds of rings called integral domains and fields that are not so weird. And we're happy about that. You should be happy about that. Smiles. They're not so weird. In particular, one nice thing about them is they do not have 0 divisors. But what is a 0 divisor? First of all, I'll just say it. These have no 0 divisors. But what is a 0 divisor? What is a 0 divisor? A 0 divisor, call it A of a ring R is a ring, is a non-zero element of the ring. Non-zero element such that there exists another non-zero element of the ring another non-zero element with A times B equaling 0, or B times A equaling 0. I'm writing this as if the ring is not commutative, that A times B could be different than B times A. Technically speaking, when in our class at least, when we talk about divisibility in rings, we are mostly restricting ourselves to Commutative rings. Let's call this a commutative ring. Then A times B will equal B times A. Because if you don't restrict yourself to commutative rings, then you might have to talk like about left zero divisors and right zero divisors. Like if AB were zero, but BA were not zero, then A would be a left zero divisor and B would be a right zero divisor, and that just gets unwieldy. We mostly want to avoid that in here, even though it does happen, like in matrix rings. A zero divisor is a non-zero element, such that there's another non-zero element where the product is zero. By the way, this would also mean B is a zero divisor too. We don't like it when this happens because it causes, for example, polynomial equations to have more solutions than expected. And we just don't like that. It's interesting, but that's not our main point of emphasis. It's just weird. We don't know how to handle it. An integral domain for us is a commutative ring with unity. There's a 1 in which every non-zero element, in which there are no zero divisors. Here it is again. An integral domain is a commutative ring with unity. We like it to be commutative, keeps things simple. We like it to have a unity. We'd like the number 1 to be in there, or the matrix 1 if it's a matrix ring, or some other, the polynomial 1, the constant polynomial 1. It doesn't have any zero divisors, which ends up implying something really important. It ends up implying that cancellation works. Let A, B, and C be an integral domain. If A is non-zero and AB equals AC, then B equals C. You can cancel the A's without multiplying by A inverse. A inverse may not exist. A may not have no multiplicative inverse in the ring. That's really key to realize. We're saying in integral domains that this cancellation of the A's works even if A inverse does not exist. You can't prove this by multiplying both sides on the left by A inverse because it may not exist. And in fact, the proof is short and it doesn't use an A inverse. It uses the fact that the integral domain has no zero divisors. Very short proof, could put on the test. Okay, you should study this and be able to prove it. It's very short. That's nice. There's another special kind of ring called a field. What's a field? We'll look at the definition here in a second in the book. A field is the most special kind of ring. Again, all rings are abelian groups under addition and never groups under multiplication. However, fields have the property that the non-zero elements form a group under multiplication. A field is a commutative ring with unity in which every non-zero element is a unit, is how it's phrased here in the book. Remember what unit means? It has a multiplicative inverse is what unit means. Commutative ring with unity. Commutative means with respect to multiplication. It's got a unity, it's got a 1, it's got a multiplicative identity. And every non-zero element is a unit. Every non-zero element has a multiplicative inverse, an A inverse, so to speak. This would mean fields are, in fact, abelian groups under multiplication when you take out 0. 0 messes it up to say it's a group under multiplication overall, because 0 never has a multiplicative inverse. Can't divide by 0. But if you take away 0, then what's left does form, in fact, an abelian group under multiplication. Abelian because we're assuming it's commutative ring. Any finite integral domain is a field. So it's going to turn out that ZP is a field. That's a finite integral domain. Its elements are 0, 1, 2, 3, etc. through p minus 1 under addition and multiplication mod p. It's an integral domain. It has no zero divisors. It also turns out to be a field. That general theorem would be enough to prove that. Any finite integral domain is a field. All the non-zero elements have multiplicative inverses. They are all units. However, careful, that theorem that I just showed you in the book does not apply to this ring. ZPX, all polynomials of arbitrarily high degree with coefficients from ZP, while it is an integral domain, it's not a field. In fact, polynomial rings of this form, where x is a true variable, you might say, and it can have an arbitrarily high degree that can't be reduced, are never fields. Polynomial rings like this are never fields. Because once you get to a degree higher than 0, once you get to a non-constant polynomial, it won't have a multiplicative inverse. You know, what's the multiplicative inverse of just x plus 1, for example? Find a polynomial that you can multiply that by to get 1? I don't think so. Is there a function you can multiply this by to get 1? Sure, 1 over x plus 1. But that's not a polynomial. So polynomial rings like this are never fields. They are integral domains when p is prime. They have no zero divisors. But they're not fields. Any non-constant polynomial is not a unit, does not have a multiplicative inverse that is a polynomial.